Good day, dear colleagues. My name is Anastasiia Kornilova. I am from Skolkovo Institute of Science and Technology from Mobile Robotics Lab, and today I will be talking about the research work and the dataset that we provide to community, which is called SmartPortraits, DEPS-powered handheld smartphone dataset of human portraits for state estimation, reconstruction, and synthesis. Nowadays, we are witnesses of active embedding of human portrait scanning into downstream AR and VR applications. Under the hood of those applications, there are more basic tasks, such as state estimation, 3D reconstruction, novel view synthesis, that are actively researched by the community. At the same time, we see active development of smartphones, in particular, continuous growth of their computational power and quality of the built-in sensor with affordable price, but they are still limited. On the one hand, those factors shorten the gap between raw smartphone data and mentioned downstream tasks. On the other, open research opportunities for applying existing algorithms on real raw data on smartphone devices and developing new algorithms. Our smart portrait dataset contains human videos that recreate in the wild conditions for smartphone users capturing human portraits. The dataset contains 200 people captured in different locations and different poses that results in 1000 trajectories. Capture is supported by external high-quality depth measurement, precisely synchronized with the smartphone video. Every record contains ground truth poses. This kit is devoted to answering such research questions as: is 3D reconstruction and neural rendering ready for real smartphone data? To record the dataset, we designed a portable recording platform powered by a NUC controller. It consists of a middle-range smartphone and an external high-quality depth camera, Azure Kinect Decay. In order to synchronize such a heterogeneous setup of sensors, we applied a twist and sync algorithm that gives sub-millisecond synchronization accuracy between smartphone and depth frames. Using this platform, every volunteer was captured in 5 different poses, captured from close-by distance to emulate selfie-like scenario, and from mid-range distances to emulate the process of scanning person by external operator. For every pose, the operator with the recording platform did 4 semicircles around the person. During the capture, we turned on the periodical flash on the smartphone for possible applications in relighting tasks. All recorded persons are captured in 5 different environments. They are lab, cafeteria, campus, office, and university. Distribution of persons per scene is presented on the right side. The scenes have native background as persons were captured in the wild. In summary, recorded data contains synchronized smartphone RGB frames and frames from external high-quality depth cameras. In addition, we provide IMU data from the smartphone for possible applications in visual inertial state estimation methods, as well as timestamps when flash was turned on to filter out lighted images for relighting task. In addition, we provide pseudo-ground truth trajectories for every record, calculated by SLAM algorithm, in particular RGBD modification. To choose reference algorithm, we considered state-of-the-art SLAM and structure from motion methods and evaluated them with the full reference metrics using the data from motion capture system on test sequences. We also applied no reference point cloud based metrics on all scenes. Colmap and SLAM demonstrated almost the same quality of trajectories up to scaling factors. Therefore, we proceed with ORP because it provides meters measurements units. In addition, we considered the task of state estimation using only smartphone data to evaluate capabilities of existing visual and visual inertial algorithms. For evaluation, we took standard trajectory metrics such as absolute pose error and relative pose error and considered 10 popular visual and visual inertial algorithms. The results of evaluation are presented on the slide. Among methods that provide real-time solutions for embedded systems that actually are smartphones, the latest SLAM visual inertial method gives the closest result in comparison to heavy visual methods such as Colmap. Thank you for your attention. Our dataset is available on our site, which you can see on the slide. Goodbye.